Assalamualaikum and hi everyone. My groups will present to you about bonding theory in transition metal complex. These are my group members. Me, Nurul Amisha Muhammad Ruzi, and my friends are Anur Anis binti Muhammad Nur Hakim, Nur Izzati Shafika binti Ibrahim, and the last one is Nur Atikah binti Cik Samsudin. So the complex that we choose to explain in this theory is called as hexaamine cobalt 3 chloride. So this is the color of the complex which is orange, and this one is the structure of the complex.
Hi, Assalamualaikum. My name is Nur Atika binti Cik Samsudin. Matrix number D2010888517. So today I would like to show you the bonding theory based on valence bond theory. So, I will explain how to get magnetic properties and spectrochemical series. For magnetic properties, if it a paramagnetism, the result of orbital field are unpaired electron, and if all pair electron, it will be the diamagnetism. For spectrochemical series, we will know if it a weak field ligand, it will be high spin complex, and strong field ligand will have a low spin complex. Let's move how we can detect it. Okay, first we know based on coordination complex cobalt exists in the 3+ oxidation state, and it has NH3 as a ligand, which is it a strong field ligand. The cobalt 3+ have a 6 electron in the d orbital based on electron configuration, and it has 4 unpaired electron. But if we look at excited state of cobalt 3+, a strong ligand field can alter the configuration of central metal ion by causing force pairing, again Hund's rule of maximum multiplicity. The energy difference between the two sets of orbital is much greater, and this energy difference is enough to allow the electron in dz2 and dx2 minus y2 orbital to move into the half field dxy and dyz orbital, even though this pairing require energy. The central metal ion in the complex make available empty orbital for the formation of coordination bond with ligand. The number of empty orbital made available for bonding purpose is equal to the coordination number of the center ion, which is 6. Since there are 6 NH3 ligand, which is 12 electrons are around the central metal ion, each of a ligand will donate a lone pair to the first 6 empty orbital. Hybrid orbital is D2sp3, which is the central metal atom having hybridization of atomic orbital, include d orbital of inner shell and sp orbital from the outer shell. So this complex is inner orbital complex that have a low spin complex and spin pair complex, which is it cannot freely spin because these d orbital are in a lower energy level than s and p orbital. Based on inner orbital hybrid, we conclude that geometry is octahedral. This complex is diamagnetic atom because it does not have unpaired electron. In the conclusion, we can know the geometry shape is octahedral. It has diamagnetic properties, and the hybrid orbital is D2sp3, which is inner orbital hybrid.
Hi, Assalamualaikum. My name is Anur Anis, and today we are going to explain about the bonding theory and electronic transition. So, for the electronic transition, we are going to explain how our complex get the color using the charge transfer. In the electronic transition, there are two rules, which are the Laporte selection rule and the spin selection rule. And for the type, there are two types of electronic transition, which are the charge transfer and the DD spin, allowed or forbidden. So for our complex, we are going to explain using the charge transfer, because using the Laporte selection rule and the spin selection rule, our complex are forbidden, but we still get the color. So we are going to explain it using the charge transfer.
Hi and Assalamualaikum. My name is Nur Izzati Shafika binti Ibrahim. For the electronic transition topic, I will talk about the Laporte selection rule. In the Laporte selection rule, it states only allowed transition are those occurring with a change in parity, flip in the sign of one special coordinate, or during an electronic transition, the azimuthal quantum number can only change by plus minus 1 or delta L equal to plus minus 1. The Laporte selection rule reflects that for light to interact with a molecule and can be absorbed, there should be a change in dipole moment. Based on the Laporte selection rule, it says that transitions between the orbitals of the same subshell are forbidden. In other words, the total for orbital angular momentum is delta L equal to plus minus 0. Also, it is forbidden because of the molecule has a center of symmetry, transitions within a given d orbitals which occur between ungirate to ungirate orbital. As for the hexaamine cobalt trichloride, the electron is excited from higher energy T2G level to the lower energy EG level, which is low spin. The orbital also same before and after the transition. This is forbidden in Laporte selection rule.
So today I will explain about the spin selection rule. So these are the graph that we obtained from the complex. It shows two transition which are at 341 nm and 475 nm. So using the spin selection rule, it states that the spin angular momentum must equal to 0, which is the delta S equal to 0, and the total angular momentum is equal to 0 or plus minus 1. Based on the Tanabe-Sugano diagram, for the D6 configuration, it shows that 341 nm is assigned to a transition of 1A1G to 1T1G. And the second band, which is the 475 nm, it shows the transition from 1A1G to 1T2G. So based on the diagram, it shows that the transition of 341 nm, which are the 1A1G to 1T1G, is allowed because it has the same state of spin multiplicity, which is 1 to 1, and the total angular momentum is also the same. But for the band 2, which is the 475 nm, it shows a transition from 1A1G to 1T2G, which are forbidden, although it has the same spin multiplicity, which are 1 to 1. But it has a different total angular momentum, which are from the A1G to T2G. So these are forbidden in the spin selection rule. So that's why we cannot explain our complex color using the spin selection rule and the Laporte selection rule. Next, my friend will explain about the color using the charge transfer. Thank you.
Hi, I'm Amisha. So we're gonna proceed with the last one, which is charge transfer. In this complex, we identify that this complex is LMCT, ligand metal charge transfer. This is because ammonia is a strong field ligand when it bonds to the center metal ion, which is cobalt. So LMCT transition are common for coordination. If we follow the origin of charge transfer like in this diagram, we can see that the ligand orbital are full. So the charge transfer are occurred from ligand orbital to empty metal orbital. Then the electron in the metal orbital are excited to the ligand pi orbital. This is why absorption is rising. So that's all for my group. Thank you and bye.